Thanks, Nicole. So this is a talk about an experimental study about the repeated secretary problem. And rather than define what I mean by that formally, I'm just going to show you an example. So this is the experimental task that participants participated in. The instructions go like this. You've been captured by an evil dictator. He forces you to play a game. There are 7 boxes. Each box has a different amount of money in it. You can open any number of boxes in any order. And after opening each box, you can decide whether you're going to open another box or whether you're going to stop. If you stop after the box that has the most money in it, you win. If you stop after any other box, the dictator shoots you. Okay? Let's play. So I'm going to open the second box first. It's got $1 million in it. That sounds like a lot. I'm going to open the 7th box next. This one has less than $1 million in it. I'd better not stop now, because I know that I'll lose. I can see that there's another box that has more money in it. This box is dominated. The 4th box has $2 million in it. That sounds like an awful lot of money to me. I think I'm going to stop. Oh, shoot, I lost. Turns out there was more money in the first box, and so the dictator shot me. Okay, respawn. Let's play this again. I'm gonna start just with the first box this time. $1.5 million, nice. Second box has $3 million, actually almost 4. Third box only has $1 million. Uh-oh, it's dominated. I better not stop. Okay, the 4th box has $8 million, and I am out of patience. I'm going to stop now. And this time I win. $8 million was the most amount of money that was in any box. Annie?
Is this the standard version of the secretary problem? I thought there was a version where you just...
One slide, please. Okay, so this is a variant of the standard secretary problem. Many of you, or at least one, have recognized that. It's a short talk, so I don't really want to belabor to you that this is a really big deal, so please just trust me. The secretary problem is a really, really big deal. It's kind of its own field, okay? However, the standard secretary problem differs from this problem that I just showed you in one important respect. And that is, in the standard secretary problem, you don't get to respawn. You only get to search the distribution once, and the distribution is unknown to you. But that's kind of unrealistic for many of the situations that the secretary problem is meant to model. Because if I'm in Boston and I want to hire a secretary, the odds are good that I have some notion of what secretaries in Boston are like. If for no other reason than that I've probably tried to hire a secretary before in the past. So this is the assumption that we relax in this setting. We, again, are searching an initially unknown distribution. However, we're allowing the participants to search from that distribution multiple times. So they're going to have the opportunity to learn about what that distribution looks like. And so the question that we're trying to answer with this study is, do they make use of that opportunity? And if so, how do they go about doing that? Okay? So I guess I've kind of previewed this. The first thing we want to do is we want to establish that people are actually learning in this setting. It seems intuitive that they would, but in fact, previous studies have found no evidence of learning in secretary problems. We're not too worried about that because they weren't actually looking for learning, because they were thinking about the classic secretary problem. And so they were doing things like only letting the participants search once, or they were manipulating the values to make it impossible to learn the distribution, or they were telling you up front exactly what the distribution was, and there was nothing left to learn. So in this study, what we're going to do is we're just going to provide some straightforward descriptive evidence that people do in fact learn, just basically by looking at how they perform on the task. The second thing that we want to look at is understanding how people actually do this task. So we're going to do that in a couple of ways. So the first thing we're going to do is we're going to construct 6 potential models that could describe how people behave. And then we're going to compare their predictive performance on our data to see which one does a better job of predicting how people act. We're going to do that in a Bayesian way. And then because we did this in a Bayesian way, we're going to be able to delve a little bit deeper. We're going to look at the parameters of the model that predicts best, and that's going to tell us more about how people are performing this task. Okay? And in particular, it's going to let us look at how play changes over time. How do people's behavior change as they learn more about the task and about the distribution? So this was an online experiment you saw our amazing UI at the beginning. Players are randomly but persistently assigned to one of 6 treatments, so they're always searching the same distribution, even though we have treatments that have differing distributions. And the data set consists of about 50,000 games, and there's about 6,500 unique users. Okay, so many of you probably know how you're supposed to play the secretary problem in the classic problem, where you don't know the distribution at all. If you do know the distribution, the optimal strategy is quite different. Okay? So the way the optimal strategy works for the known distribution is every box has a threshold associated with it. That threshold is in terms of the quantiles of the distribution. Okay? You start off with the first box you're opening having quite a high threshold, and the thresholds get lower and lower as you go. And the way you use these thresholds is as follows. You open a box. You look at the money. You see, is this money more than any of the monies that I've seen before? I.e., is it non-dominated? If so, is it bigger or less than the threshold on this box? If it's bigger, you stop. Otherwise, you carry on. Okay? So clearly, with the very last box, you're going to have to stop. With the box before that, you're going to want to stop if it's above median. And beyond that, it gets extremely complicated and kind of awful to solve, but one of my co-authors solved that for us. Hi, Preston. I see you back there. Okay, so the important things to notice about these thresholds are 2 things. They're declining, okay? You start with very high standards, and then your standards go down as you become increasingly desperate. And the second thing to notice is that, or maybe even just another way of saying this, is the thresholds are always the same for the same number of boxes. So once you know the number of boxes you have left, that tells you the quantile that you should be using as your threshold. Now, in our setting, of course, you don't actually know the distribution perfectly to begin with. So we don't want to use that as the benchmark to tell how well human agents are doing when they play this game. So instead, what we want to do is we wanted to construct a benchmark of our own. We constructed a learning agent to play this game basically as well as we could figure out how to play it. So here's how this agent works. It knows the threshold percentiles, because we know them. And so what it does is every time it sees a box, or it sees the amount of money in a box, every time it sees a sample from the distribution, it updates its mapping of quantiles. It updates its estimates of what the quantiles of the distribution look like. And it stops when it encounters a non-dominated box whose estimated quantile exceeds its threshold. This is the best we can figure out how to do. It's not quite optimal because there's some Bayesian action you could do to make that happen. This is the best how we know to actually code up. So how does the agent do? It starts off doing about, why don't I tell you about this graph? Okay, so on the x-axis, we've got the number of games that the agent has played. So we simulated up to 20 plays for the agent. The y-axis has probabilities, okay? The red line here is the win rate of the agent. So how often did it win after that number of games? The black line is the optimal win rate that you would get if you knew the exact distribution and you were playing exactly optimally. And the blue and green line represent the loss rate. They're 2 different ways of losing, either stopping too early or stopping too late. So the agent starts out winning about 40% of the time. That's very close to how it would be doing if it was using the optimal strategy for the unknown distribution. But as it sees more and more boxes, its performance increases quite rapidly. And after about 20 games, it's basically matching the optimal it could be doing if it knew the exact distribution. Humans behave in a way or perform in a way that's quite qualitatively similar, albeit noisier. So again, we've got probability on the y-axis, we've got number of games played on the x, we've got a red line representing the win rate. Black line is the theoretical optimal if you knew the exact distribution. The dotted line here is the performance of the learning agent. And the red line is the win rate. So people start off doing somewhat worse than the learning agent starts off doing. But again, their performance increases fairly rapidly with experience. Eventually they top out. They don't seem to be topping out at exactly the same level as the learning agent, but they still have a definite improvement here. And so it's pretty clear that people are learning. Either they're learning how to play the game better or they're learning something about the distribution because they're winning more often the more often they play it. So what we really want to know is how are they doing that? What are they doing with this game? So I'm going to describe to you now the behavioral models that we constructed, and then we're going to look at how well they performed against each other. So the first model that we constructed we called the value oblivious model. So this is kind of like a baseline model. The way this one works is every box has a probability of stopping associated with it. And what you do is you open the box. If the box is non-dominated, then you stop with the box's stopping probability. So notice that aside from checking for domination, you're not really taking account of how big the values are at all, which is why we call it value oblivious. The next two models are inspired by the optimal stopping rule for the unknown distribution case. So sample K opens K boxes and then stops on the next undominated box after that. So that is the optimal strategy for the classic secretary problem. And viable K is just a variant that stops on the kth non-dominated box. We looked at the multiple thresholds model. This is the model where every box has an associated threshold. It's the optimal strategy if you know the distribution. It takes the thresholds as a parameter to be fit. And then we have two simpler versions of this multiple threshold model. We've got one version where all the boxes share a threshold, and another version where the early boxes share a threshold and the late boxes share a threshold. Okay, so we compare models using something called the Bayes factor. And so all that is it's just a ratio of the posterior probabilities of the models conditioned on the data set that we have. We assume a uniform prior over models. That's pretty standard. So this quantity is going to be proportional to just the posterior probability, or sorry, just the likelihood of the data given the model. The standard way to compute this marginalizes over the parameter prior. So what I mean by that is every one of these models has parameters before it can make a prediction. And so we take every possible parameter value and look at the likelihood of the data according to those parameter values. And then we take an average. And the average is weighted by the prior probability of each of those parameter values. Now we're not really training, thank you, we're not really training the model at all here based on data. So what's going to happen is you're going to wind up averaging in a lot of really terrible parameter values. This actually has a desirable consequence, which is that high dimensional models will be penalized because the higher your dimension of parameters, the more terrible parameters we're going to average in. That's kind of desirable because higher dimensional models are more prone to overfitting, and so you're going to tend to prefer models that are simpler. However, that's not what we do. Instead, we use something called the cross-validated Bayes factor, which is very similar, except that what we do is we first divide the data randomly into a training set and a test set. We update the prior against the training set. So now we've got a posterior distribution of parameters that has been sort of trained on the training data. And then we take the average likelihood of the test data computed against this posterior instead of computed against the prior. And what this does is it penalizes overfitting directly instead of using this proxy of the high dimensionality. Because if you have a posterior that really likes the training data, but that's because it fit a bunch of noise in the training data, you're going to do poorly. And that's exactly what we want to have happen. So this is very much the same sort of justification as you would have for a standard kind of cross-validation, but you still get to get a probabilistic interpretation of the comparison. Okay. So how do the models do? Once again, we've got some axes. So let's talk about those. On the x-axis, we've got the number of games played. So we're going to fit these models individually for each step of the way as a player plays more and more and more games. On the y-axis, we've got the cross-validated Bayes factor. Now, we've got a lot of models here, so rather than show you all the pairwise comparisons, what I'm doing is I'm normalizing to the worst model. So this is what is the Bayes factor for this model versus the worst model for this number of plays. So higher is better. And so what we can see is that for the first game, and the second game as well, the model that performs best at predicting what people are going to do is the value oblivious model. Which makes sense, because people just don't know even what's going on when they're first starting out. People are acting pretty randomly. Subsequently, however, the multiple thresholds model performs best. And that's actually quite exciting, because that's the optimal kind of model. That's the optimal decision rule to use in this setting as you learn about the distribution. Thank you. So good job, people. So it's nice that we're using the optimal decision rule, but are we using it well, right? What thresholds are people using in this multiple thresholds model? So we can peer under the hood here as well and look at the posterior distributions of these parameters. And what we find is that, okay, here again, we've got the number of games played, we've got the estimated thresholds on the y-axis. These stars are the theoretical optimal thresholds. And what we see is that in the first game, things are terrible, they don't make sense, but subsequently, the thresholds are correctly ordered. And what I mean by that is early thresholds are higher than later thresholds. They're all in the correct order from the second game onward. Second of all, as people get more and more experience, these thresholds start to get closer to the optimal thresholds. And in fact, after about the fifth game or so, the optimal threshold is contained within the credible intervals for each of these thresholds. Now, I don't have time to talk about this first box, which is sad, because this also tells us something. This misordering in the first box actually gives us, evidence in favor of the value oblivious model for the first box. So even by looking at the fit for the multiple thresholds model, we can learn something about how probably it was a different model for the first box. Okay. So to wrap up, we established that people learn in the repeated secretary problem. I just showed you some straightforward evidence that people's performance increases, but we provide other evidence of that in the paper itself. And we characterized human play. We showed that people use something like the optimal decision rule, and they use it in something like the optimal way. And so that's a rare thing to be able to say in behavioral research. So can we just pause for a minute and feel warm and fuzzy that people haven't screwed this one up? And so one of the pieces of this work that I'm especially excited about is the way in which we examine these models, because we were able to say a lot more using this Bayesian analysis than we would have been able to if we had just looked at the accuracy of the models or something like that. Okay. So previously, I spent a lot of time working on predicting how people are going to play the first time they do something at the population level. This work talks about how play at the population level evolves as people learn about the task and repeat the task. And going forward, we're looking at extending this to modeling how individual play evolves. So can I tell from how somebody was behaving in an early iteration of this game, how they're likely to behave in a later iteration of this game? So that's kind of the direction that we're moving with this work. All right, so thank you very much for your attention.